Hello, my name is Scott Grizzard from the University of South Florida. This is Lecture 6B, Calculus 1, Implicit Differentiation. Before we begin, though, let me give you a warning about implicit differentiation. It's one of those things that is simple but hard. So some people will find it easy. Others are going to find it unsettling in a certain sense, and that's okay. So just read through it again, work through it again, work through some more problems. If you find this difficult, come see me during office hours. That's great. And we'll talk about it because, as I said, some people find this a little unsettling. Others are like, yeah, this is awesome. And I want everybody to have that, oh, yeah, this is awesome. But some people are going to have more work required than others to get to that point where they're just like, oh, I see. So just heads up about that. Okay, so what we want to do today is we want to talk about implicit differentiation of curves. And the example that everyone uses is lines tangent to the unit circle. We'll talk about the method of doing it. We'll do the unit circle example. First, we'll do it the explicit way, the way we've been doing it, where I actually solve for one of the functions, right? Because I can break the unit circle into two functions, and we'll see that. And then what I want to do is I want to talk about how you do it implicitly, so what the method is for doing it. And it's a very powerful method, so I'll actually talk about some of its power. Then we'll mention the implicit function theorem, but I say again loosely because this is really a Calc 2, Calc 3 topic. And that's sometimes why people find this difficult, is because the justification for why it works is really something you need parametric equations for. That's something you do in Calc 2 and Calc 3. So again, some people are going to find this extremely natural and be like, others are going to be like, why can't I do this? So we'll just talk about it a little bit. Then we'll do some more examples. We'll do the Folium of Descartes, which is, always a cloud freezer. And then we will do the power rule for rational integers, the actual proof of that. I'm sorry, the rational exponents. So we'll do the power rule for rational exponents at the very end and the proof for it, which is very clean and nice, but you need implicit differentiation to really do it. So the big idea, these are the big ideas. I can implicitly take a derivative anywhere I can pass the vertical line test locally. So if I can make my graph small enough, I can take an implicit derivative. What I do is I take the derivative of both sides and I never forget the chain rule. The chain rule is what's driving all of this. So let's look at that. And remember the notation, f prime of x equals dy over dx equals the derivative with respect to x of y. Okay, so let's look at some examples of last time we did this chain rule. And one of the last things we did with the chain rule was we had a chain rule with unevaluated terms. So remember, the chain rule is the thing that lets me change this. So let's suppose here, t moves with s. So I've got a derivative with respect to s of t squared. And I know that when I move s, t is going to wiggle. So it's not just zero. It's not just the derivative of the constant. I know that t actually moves. So when I do this, I have an unevaluated term when I do the chain rule, right? When I do the chain rule, I'm going to get d over ds of this whole thing, the u, right? I'm sorry, I'm going to have d over dt. And let's actually write this out. So when I do the chain rule here, I'm going to do d over dt of t squared times d over ds of t. So when I did the chain rule, it allowed me to change the variable by which I was differentiating. Okay, so when I do that, when I evaluate this, right, d over ds, I can't do anything with. I have to use the chain rule. And then when I take the derivative of this, I get 2t times the derivative with respect to s of t. Well, I don't know anything about t except that it moves with s. So I just write this as dt over ds. Likewise, if I have the derivative with respect to v of u plus v, by the sum rule, this is going to be the derivative with respect to v of u times the derivative with respect to v of v. And the derivative with respect to v of u is simply du over dv, and then the derivative with respect to v of v is simply 1. And I can do here the product rule. D over dx of x times y is going to be the derivative with respect to x of the first times the second plus the first times the derivative of the second. This is going to be a 1. This right here is going to be an x, and here I've got an unevaluated dy over dx. Okay, and I can leave that as just y plus x times dy over dx. Okay, so that's the big deal with the chain rule. Remember, I can have unevaluated terms in my derivatives. Let's look at the slopes of lines tangent to the circle. So here I've got a standard, x squared plus y squared equals 1 circle. And let's compute the line tangent, the slope of the line tangent to the point 1/2 square root of 3 over 2. So this is, the usual pi over 3 around, and I come to this point, and I want to know the slope of this line tangent to that point. Okay. So the answer will be -1 over square root of 3, but let's see how we do that. Now, if I wanted to do it explicitly, what I would do is I'd create a function. And so I'm looking right now, I could create a function here. I'm going to look at the top part of this thing, because this thing's not a function. The circle is not a function, right? It doesn't pass the vertical line test. But I can split it into 2 functions here. I could split it into a top function with the formula of the square root of 1 minus x squared. And then if I so desired, I could have a bottom function here. And then this right here, for the top function, this is the line we want is right here. So what I do is I compute the slope of that line. The slope of the line tangent to the curve would be the derivative of this function at 0.5. So what I need is f of 0.5, where this right here is f, right? The whole circle itself is not a function, but the circle, the half circle is. So that's what I'm going to do. I'm going to set f of x equal to the top half of the function, and I'm going to compute the derivative. So when I do that, again, if I wanted the bottom part, it'd be negative, but I want the top part because my y is positive. So I do that, I'm going to get f prime of x equals the derivative of 1 minus x squared to the 1/2. Okay? That gives me the derivative of u to the 1/2, right? I've got a little chain rule here. I'm going to say this is u, and then I'm going to do a chain. So I'm going to get d over du of u to the 1/2, the change in u caused by, the change in u to the 1/2 caused by x is the change in u to the 1/2 caused by the change in u, times the derivative with respect to x, the change of u with respect to x. So this piece right here, I evaluate using the power rule. I get 1/2 u to the -1/2 times the derivative with respect to x of 1 minus x squared. Yada, yada, yada. When I take that derivative, I'm going to get 0 minus 2x. And then when I sub in here my baggage, and I'm going to get, the 2's are going to cancel here. I'm going to get 1 minus x squared to the -1 over 2 times the negative x. I'll put the negative x on top. I'll put this on the bottom and put the square root back there. So that's how I would solve this problem. I take the derivative, and now I throw in 1/2. So f prime of 1/2, blah, 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 blah. I'm going to get -1/2 over the square root of 1 minus x squared. 1/2 squared is a quarter. Blah, 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 algebra, 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 algebra. And I wind up with, flipping that, and I wind up with -1 over the square root of 3. And that's how I would solve this problem traditionally. But notice how it depended on the idea that I could split this thing up as a function explicitly. And the circle's relatively easy to do that. There's another approach, though. And the other approach is to do it implicitly. What I'm going to do is I'm going to just leave that function like it is. And then I'm going to find an expression containing dy over dx, which is what I want, right? I want the slope at that point. So the implicit way is to do this. Okay, I've got my equation, which was x squared plus y squared equals 1. Now I'm going to take the derivative of both sides. So I did d over dx of both sides of this equation. Now, when I do this, a little sum rule is going to break that up for me nicely. And the derivative of x of the one function is simply 0. All right, so now I've got this. This I can solve with a power rule. This one right here needs a chain rule. Okay, this right here, I've got an x here and a y squared here. So I can make y my u, but I already have a variable for it. It's y. So when I do this derivative, what I'm going to do is I'm just going to take the derivative with respect to y of y squared and then account for the change in y caused by x by multiplying. Now I'm going to use the power rule again, right? I've got d over dy of y squared. That's power rulable. And this is just going to become the unevaluated derivative, just like up here where I had unevaluated terms. Now I'm going to exploit the fact that I can do this. And I'm just going to leave an unexploited dy over dx. And notice that's actually the slope I'm looking for. Now, I could solve for dy over dx explicitly, but I don't actually want that right now. All I want is the slope of the line tangent to the point 1/2 the square root of 3 over 2. So what I'm going to do is I'm going to say, okay. Now, notice here I need both the x and the y. So here I have an equation with both an x and a y in it. Over here, I didn't. Here, when I ended up solving, I wound up with just an equation with x's in it. But this thing could not handle y's that were negative. I'd have to recompute the derivative. This thing doesn't care where y is, as long as y is somewhere where a derivative would exist. It doesn't care. So I don't have to sit here and figure out what the function would be. I just derive it implicitly. So now what's going to happen? Well, I'm just going to sub in my variables. So I've got x is 1/2, y is square root of 3 over 2, and then I've got a dy over dx, which I'm just going to call m. Now I solve. Well, this is easy. This is going to be a 1. Move the 1 over to the other side. And there's my answer. That's what my m is. And if I want the whole tangent line, I simply plug it in. The tangent line is going to be y. So if I wanted the whole tangent line, that would be it. This is y minus y naught, and all I did was move it over to the other side just in general. And we're going to learn that later. If you look at all of my little graphs, when I do these, you see that I plug it in, this function right here. This right here is a functional form of the equation of the tangent line, right? Here's f of a, right? This is L of x minus f of a equals f prime of a times x minus a. A is the x naught here, and all I've done is this f of a is the y naught. I've just moved it over. And then there's the slope, and then there's x minus a there. So that a in this case is 0.5. And that's how I got my tangent line here. Okay, so that right there is the equation for my tangent line. That's nice. Now, it should be, so here's what I did. I didn't need to do any of those steps. We are going to do those things later, but not right now. What I did was I took the derivative of both sides in terms of x, and I allowed the chain rule to leave unevaluated dy over dx lying about. I actually looked it up. It's lying, not laying. So I leave these unevaluated dy over dx terms just lying around. Then I algebraically manipulated and substituted. So what I did was if a slope at a point is needed, I let m equal dy over dx at x naught, y naught, which is what I did right here. And then I subbed in my x naught, my y naught for x and y, and I solved for m, which is exactly what I did here. So these are your steps. Now, I could have solved for a general derivative of dy over dx. I could have done that. If I wanted it right here, I could have done this. So this right here is me just saying, I got what I need, right? All I needed was an expression with dy over dx in, and then I could plug in numbers. And usually, if all you want is the slope at a particular point, this is the better way to do it, because you sub in numbers and sometimes things cancel and it works out nicely. However, if I wanted to solve this for the general dy over dx, I would take this step where I had 2x plus 2y dy over dx. I would simply solve this for dy over dx. And that would be done, right? Now, here's something else that's interesting. So I just solved for dy over dx. Now, notice this dy over dx works either way. Even if y is negative, right? This equation didn't work if y was negative, right? This was only the top half of the circle. This thing works no matter what. So, well, not no matter what. It doesn't work right here, but it works for the rest of the points. I can get this nice little equation for the line if I'm there, or I could slide this around. Oh, I can't slide it around. Now I can slide it around. So I can actually slide this around the whole circle and get my tangent lines not just on the top half, but on the bottom half as well. Okay. If I wanted to solve for the general equation there. Now, notice one other thing. It's actually, you see this y? If I came back to my other equation, y, or f of x, equaled the square root of 1 minus x squared. That's the bottom here. So y actually equals the square root of 1 minus x squared when I'm at the top. So this equation right here comes to the same thing, except it's restricted to y values that are greater than 0. This whole thing was the exact same thing, except it didn't give me the whole circle. It only gave me the top half. So let's talk for just a moment about why this works, okay? It is called the implicit function theorem, and you'll see pieces of it in Calc 2, and then you might prove it in Calc 3. You might not, depending on, where the instructor is. But you need parameterization. So the idea here is that what I could do is I could express these x's and y's in terms of some t, okay? And if you think about t being the position on the unit circle as I run around, it's sort of obvious that what I'm going to do is I'm going to use cosine of t for the x value and sine of t for the y value, right? So then I can express this thing as a function of, as an output with two different variables. And then what I can do, and that's basically what you're doing when you do it. There's some technical details in here that I'm skipping over. However, basically the function says this. If I'm centered on some x value, if I can zoom into the graph so much that what I see passes for the vertical line test, then I can take the derivative of both sides in terms of x. So if we look at my circle example again, right? Here, I'm not passing the vertical line test, right? I've got I've got 2 points here for that x value. But I can zoom in, and look, I've zoomed in enough that now my graph passes the vertical line test. Matter of fact, there's only 2 points here where I can't do that, right? And that's when this y value here equals 0. When the y equals 0, no matter how much I zoom in, I can't get rid. When y equals 0, I cannot, even if I stretch it and deform it, no matter what kind of stretching here that I do, look at this. It's still right at that point. There's no way for me to zoom in close enough to pass the vertical line test. Here I can. If my point is right here, I can actually zoom in enough and rebox it to make the vertical line test work. But there's no way, if this thing's on the interior, that there's no way that I can possibly zoom in enough to make that little bit of curve go away down here. Okay, there's no way to do it. So I have a derivative everywhere where I could pass the vertical line test and where it's unambiguous. And I'll show you what I mean by ambiguous later. Okay, so that's basically what the implicit function theorem says. It says that if I can make it so that I pass the vertical line test locally, I can take the implicit derivative. All right, let's see if we can't reset this. Okay, you can actually see a little bit of why it works, because what I've done here is I've set up the thing, right? This right here is the exact same curve. I've just set it up in terms of cosine t and sine t and let t run around. So I've now defined a function of, the points are all functions of another variable. And then what I do is I divide the derivatives of each other, and that will give me the derivative that I wanted. That would give me dx over dy. But there are technical details that you have to check. So as I said, you'll see a bit of this in Calc 2 when you do parameterization, and then you'll see it again in Calc 3 when you do partial derivatives. Okay, so we've talked about why it works. What can it do for us? And remember, the chain rule is the center of this. It's what lets me change the variable. Okay, so let's talk about what it can do. This thing can compute derivatives of curves that are not functions everywhere. So, and a lot of times I can compute the derivatives of things that I can't stick in terms of I can't make functions. So it computes the derivatives, I should even say that, of everywhere, even things that cannot be expressed as functions of one variable. And there are such things. And so in real life example, things like labor supply curves, they tend to bend backwards. So if you play around with it, you can actually see how powerful this tool is. Another place where this tool is very powerful, if I want to simplify the algebra of some things. So let's go back up to here. If I have this thing, dy over dx equals negative x over y, and that works for the whole curve, I don't have to take two separate derivatives. Here, notice I would have to take two separate derivatives. I'd have to take f of x equals the square root of 1 minus x squared to deal with the top half. And then I'd have to do f of x equals negative square root of 1 minus x squared. So I'd have two different things, two different derivatives depending on my case. This is much simpler. This is just dy over dx equals negative x over y. It lets me simplify algebra. It also lets me, it's going to let me prove the power rule for rational exponents. It's later going to let me prove the other version of the power rule, which is just for real exponents. So we'll get logarithmic differentiation out of implicit differentiation. It'll let us compute the derivatives of arc sine and arc cosine. It's going to let us compute derivatives for inverses in general. And it's going to let us compute weird derivatives. So it's going to let us, we're going to have some things, right? These are things that I don't have calculus for yet. I have to do algebraic manipulation first. So it allows us to do a lot of really cool algebraic manipulation and then take the derivative of things. And then it allows us to compute the varied rates. In other words, it lets us do all the math for the rest of Module 2 and some of Module 3. So it's a very important technique. Okay, let's look at another example. This one's called the Folium of Descartes. And its equation for this particular folium is x cubed plus y cubed equals 4xy. Now, here we've got the folium here. We can actually see it plotted here. What I want is I want the slope of the tangent of the line tangent to the folium at 2, 2. Now, looking at this, you can actually see that here, all throughout this, I have an implicit curve, right? I can zoom in close enough onto 2 so that I have a function. Moreover, there are a whole bunch of other points that I can do this to as well. There's a point right here that I can't do it. And then there's another point around 0 here. Not only can I not, not only is it locally not a function, it's not even a curve in the traditional sense, right? They cross each other. So the folium of Descartes looks like this. And what we want to do is we want to discover, we want to algebraically discover the line, the slope of the line and the equation of the line tangent to this curve, to this point right here at 2, 2. So let's look at how we do that. Okay, so what we need is we need the y1, we have, I'm sorry, the y naught, which we have 2, the y1, which we have 2, I'm sorry, the x naught that we have, which is 2, and then we need the slope of the line. So to find the slope, we're going to implicitly differentiate this. So I took the derivative of the both sides. Now, this one is going to be a sum rule. There's going to be some chain in here, but this side is actually pretty straightforward. But notice this side, I've got an x and a y, but y moves with x. So this is actually on the right. I actually have a product. The 4 I can pull out, but the x and y, both of those move when x moves. So I've actually got a product rule on the right. And notice there's a reason why I wanted to use d over dx instead of primes when I did this. Because using d over dx actually tells me what variable I'm differentiating in terms of. So it's a nice bit of bookkeeping. Okay, so I've taken my implicit derivative. Now, I could solve for this. Now that I've done this, I could solve for dy over dx, and there's the work that would get me there, right? I think I erased my 3 by accident. Yeah, because there it is. Okay, I just accidentally erased the 3 there. So I could solve for this if I wanted to. But notice I don't actually need this. I don't need a general equation for dy over dx. All I need to know is what's going on at 2, 2. So I'm going to go ahead and sub in everything, right? So y naught equals 2. And m is just going to equal the dy over dx at 2. So now I'm just going to sub in here. Everywhere I see an x, I'm going to plug in a 2. Everywhere I see a y, I'm going to plug in a 2. And everywhere I see a dy over dx, I'm just going to plug in an m. And then I'm going to solve for m, but I'm actually going to have numbers to play with. And that will encourage things to cancel and work out for me. And I like that. So I'm just going to just sub it in. Okay, well, that looks nice. What's really nice is that this is going to be a 4, that's going to be a 4, and that's a 4. Ooh, I like that. Let's do that. So what I'm doing here is I'm going to factor out the 4 on both sides and cancel it. I do like those. So now I'm left with 3 plus 3m equals 2 plus 2m. Move that 2 over there. Move that 3 over there, and I'm going to get that. Actually, I'm going to do it the other way. I'm going to move the 2 there, so I get an m on this side. And then I'm going to move the 3 by subtracting over there. I'm going to get a negative 1. And that's it. I didn't have to solve, right? This has, I mean, it's not horrible algebra, but I don't have to do it. If I don't want dy over dx in general, I don't need to do that. All I need to do is solve for the slope that I wanted, and there's the slope. Now I've got the slope, I can do the tangent line, right? So my equation for my line is, and I've got my m here, which is negative 1. I've got my y naught, which is 2, and I've got my x naught, which is 2. And if I want to verify what's going on here, I might check the x-intercept. I'm sorry, solve for the y-intercept. And to do that, what I'll do is just work it out. Now, I don't need to. I've already found the line, so. But I can do it. And if you look at this screen over here, if you look at what I did here when I did this, notice here I actually did exactly that. I've got y naught here plus m, right? Because I moved the y naught over to the right side. And then I've got this equation, right? I've got y naught plus m times x minus x naught. And that would be a y, but I'm using L of x because it's a function. And that actually gives me the function for that line. So I'll just go ahead and solve. So I'm actually done, but if I wanted to see what the intercept would be, I could do that. And that would be the equation. And the thing would cross at 4, which is indeed where my y-intercept is. So I can solve for the y-intercept if I want to verify what I have. By putting it in slope-intercept form. Okay, so that's the Folium of Descartes, and the big example. You'll find it in, I think, all the textbooks. It's a pretty famous one. And it's nice because it's got this product rule on the right that you have to watch out for. So if I look at the journey of x, let's see what that looked like, right? I have an x and I have an x. I have a y. I multiply it by 4, but I've got a product on this side, right? I got a product. Here's a chain. Here's a chain here. This is a sum. I don't actually care about that because those are just doing them together. But here's another chain. So I've got some things going on with this, but watch out for that product because both of those move with x. So just be careful. Okay, so we did, a couple of big implicit differentiation applications. We did a Folium, we did the circle. We talked about how we can do these things geometrically. Let's talk about some of the big power for this. So what we're going to do is we're going to use implicit differentiation to prove that the power rule works for rational powers. So this is the proof that I can do this, right? The derivative with respect to x of x to the 1/2 is 1/2 x to the negative 1/2. So in other words, I can use the power rule to do things with fractional exponents, wherever those fractional exponents are defined, or wherever the fractional exponent -1 is defined. So recall that a is rational. So I've got a is a rational number if there exist integers p and q not equal to 0, so that a equals p over q. So 1/2 to 1/3, 756 over 238 plus 3. Right. All of these are numbers that can be expressed as ratios of integers. So what we've done already for the power rule, we proved it worked for integer powers. That was in lecture 4b. We used the binomial theorem to do that. So this week, as it's coming to a close, or week 6, we proved that it works for negative integer powers because we proved the reciprocal rule using the chain rule. And then we use the power rule for positive integers and the reciprocal rule to show that it worked for negative integers. And that's on problem set 6. Now what we're going to do is use implicit differentiation to show that it works for rational powers. Next week, problem set 7, we're going to show that it works for real powers if x is positive, and we're going to use implicit differentiation with logarithms called logarithmic differentiation to show that. So we're actually going to do all the power rule proofs in this class. Okay, so let's get to and this is a pretty, it's got some bad algebra in it. There's kind of an algebra thing, but it's overall a very nice proof. What we want to show, so let's suppose I have p and q be integers, q not equal to 0, with f of x equals x to the p over q. Then I'm going to say if p over q x to the p over q -1 exists, right? So like the derivative of the cube root of x does not exist at 0. You get an infinite slope. Then f prime of x equals p over q x to the p over q -1. So my strategy, I'm basically going to go down the list. This was from before. There we go. So what I'm going to do is I'm going to change f of x to y. I'm going to do a little algebraic manipulation. I'm going to take the derivative of both sides. And then I'm going to solve for leaving the unevaluated dy over dx. Then I'm going to solve for dy over x, because what I'm after is the general derivative. And I'm going to sub back in my y. Right? This is the thing I desire. So we're just going to get rid of the other one. All right? And sub back in your more y, because I created it. So, and then one of the little algebra thing is that I'm going to need to split the terms, and then what I'm going to need to do is just move everything to the same level. And I'll show you what that means in a minute. Okay, so in general, we'll just start out like it says. All right, let y equal x to the p over q. Now I'm going to take the qth power of both sides, and I'm going to have y to the q equals x to the p over q to the q power, which is simply x to the p. Now I'm going to take the derivative of both sides, d over dx. Now, x to the p here is now an integer, because I assume that p and q were both integers. Right, since both of these are integers, I can use what I already have. Let's do the chain. Okay, so now, by using that integer power rule there, I've now solved both sides for this derivative. I'm sorry, I've now taken the derivative of both sides, and I have qy to the q minus 1 times dy over dx equals p x to the p minus 1. Well, I'm going to divide both sides by the left, and then sub back in for y. Okay, well, now I have x to the p minus 1, y to the q minus 1. I'm going to move the q minus 1 to the top and split it up. And you'll see why in a moment. So this becomes p over q, x to the p minus 1. I'll leave the p minus 1 there. Y to the, now y to the q minus 1 is y to the q times y to the negative 1. Well, the y to the negative 1 will become a y to the positive 1 when I move it up. Okay, so let's do that step explicitly. This right here is y to the q times y to the first. Sorry, y to the negative first, because it's y minus 1. Well, when I move it up to the top, the minus 1 becomes just a 1. Okay. Now what I'm going to do is sub back in y. And y was x to the p over q. So what just happened there? Well, I've got y here. I subbed it back in. So this y to the first became x to the p over q. This x to the p over q to the negative q. This right here is going to, those are going to cancel. I'm going to have x to the p minus 1, x to the negative p, x to the p over q. Well, now what I'm going to do is I'm going to obey the exponent rules and simply add all these exponents together. Now, look at what happens to these exponents. This one goes away. Those two cancel. Those two become a 0, right? P minus p is 0. And I've got a p over q positive and a negative 1 there. So thus I get dy over dx equals x to the p, I'm sorry, I lost my p over q, didn't I? I forgot about him. He's there all by himself. He was baggage and I dropped him. Okay, so now I'm going to get p over q, x to the positive p over q minus 1. And that's what I wanted to show. And that's it. That's the power rule for rational exponents. Okay, so today what we did was we played around with implicit differentiation. We used a bunch of its power here. We did the example with the circle. We talked about the method. We talked about the implicit function theorem a little bit. And then we actually proved, we did the Folium of Descartes. And I made this point here that you have to watch out for things like power rules. I also made the point that if what it wants is something specific, you don't have to do all this stuff to actually solve for dy over dx explicitly. If what you actually want is just what's going on at a particular point, right? You can actually just start subbing in once you have an equation with d over y over dx in it. Okay, so there's why I found the equation of the tangent line here. And then we did the power rule. Next time we're going to do more implicit differentiation, but we're going to use logarithms. So that's called logarithmic differentiation. Okay, so that's it for me. Have a good day, and I'll see you guys next time.